All right, everyone. We are on General Relativity Part 5.
Wax your arm stream.
What? Wax your arm stream? No. No! Why? Oh, let's do this too. Festive. General Relativity Part 5. Let's talk about last time. How come this won't connect? You're driving me up a wall. So we are on General Relativity Part 5. Last time, we taught, and I will do it last time this time, because last time, I didn't do it last time, and I had to do it last time. So this time, we'll do it last time. Okay. So we defined a tensor, and we had some different vectors and stuff inside the tensors and covectors, and we wrote it down like this. We have something that acts. We can have it act on a bunch of vectors and covectors, and the rank of the tensor is basically how many vectors and covectors you would need to act on that tensor to get it to map it to the reals. So that was the rank of the tensor. And here we can see something like that where we actually apply some tensor to a group of vectors and covectors, and we can and that will give us some sort of answer, some sort of real number if we map out that tensor. Now, we figured out we could change some indices. So one thing that we could do is see gamma was equal to the metric, and we're going to use the different metric symbols. So right now we're using G from Hartle, but soon we'll end up going to N from Carroll. So just bear with me as we do this different. We do this different thing. Really, it's strained enough, but the next half a wave is going to squeeze the system that just stretched. Oh yeah, I see what you're saying, but okay, so we'll talk about it on Discord because that's loaded right there. I think that's an interesting point that you brought up. And by the way, if you guys are tuning in, I do have my notes on Discord. Feel free to hop !Discord, hop in the Discord and grab these notes if you want to follow along. So you don't have to write them down. You can just read what I'm writing. And follow along, ask questions in chat, and we'll get to it. So we can actually change the indices. So for instance, if we want this tensor to be all bottom indices, we can actually write that. So T, alpha, beta, and gamma can be expressed as the metric times. Metric, which would be gamma delta times T alpha beta and then delta. So here we have this metric. And then we can change this index to bring it down by multiplying by the tensor. This delta will contract, and you can sum over those indices, and what you'll get is a lower tensor. So you get a different matrix completely, because we know that tensors can be written as matrices, and you can get a different one completely if you do that. Well, rank 2 in tensors can be written as matrices. So we also talked about defining the delta function. So we had a new definition of the delta function where we can write it as metrics. And remember, these are Hartle metrics. So they're the -1, 1, 1, 1. G alpha gamma times G gamma beta is equal to delta alpha beta. So we can write this, and this is a rank 4 tensor, or not a rank 4 tensor. This is a rank 2 tensor with oh no. This is a rank 2 tensor with in 4 dimensions, right? So we can talk about so one thing we need to, oh well, we'll get back to that in a second. So before we talk about that, let's make sure we finish our last time. As well as we can talk about the Levi-Civita. We talked about that last time too. The Levi-Civita was, Carroll has it as a 4 index. And we had some discussion about when was that relevant. I don't think we ever realized when it was relevant or not. But if it's an even permutation of the indices, oh, I should write the indices. So we have mu, nu, rho, sigma. And if it's, so if even cyclical, permutation, then it was +1. If it was an odd cyclical permutation, if odd cyclical permutation, then it was -1. Otherwise, it's 0. Okay? So that means that if we had, say we had the indices 1, 2, 3, this was the example we did last week. If we had the indices 1, 2, 3, right? Then, if it was 1, 2, 3, then you know, any that would be what we would call. Let's be more general. Let's say IJK. Say IJK. So if they were IJK, then it was +1. If, you know, IJK were cyclical, it would be -1 if they weren't cyclical, and it would be 0 if they were, like, if there was 2 I's or 2 J's or 2 K's or anything like that, right? So for an example, if we had IJK, that would be +1, right? If we had epsilon IKJ, is there any way we could permute these in a circle? You know, in a circle to get, permute them around, I don't know about a circle, but permute them around in order to get IJK or IKJ, and the answer is no. In order to get that, you have to switch the place positions with these. You can't permute K through. So this was equal to -1. What about JKI? Well, yes. Welcome to the channel. You can permute that. Weird. Classic Nations, welcome to the channel. Thank you for the follow. So so we can permute these around by just saying, if we take the I and move it to the back, then that's a cyclical that's an even cyclical motion, so that's +1. So this is the Levi-Civita. We talked about that last week as well. All right then. So we had that. Now, a few more useful tensor ideas that we did not talk about. Oh, we still have to do the food thing. Don't forget to remind me to do the food thing. We can do it on Discord if you guys want to. That's fine as well. But don't let me leave without figuring out some plan to do the item of cooking for our cooking stream on Sunday. Okay, now. So a few ideas that we have that are helpful are symmetry versus asymmetry, symmetry versus, anti-symmetry. Now those two things are very helpful. We could talk about the way the indices are. So we have symmetric indices. So the symmetry in the tensor, in the indices, looks like the following. So if we can move tensors around, or move indices around, and not change the state of the tensor. So for instance, we could say that, we could say this is true, right? Where the tensor looks the same, regardless of switching the indices around. Okay, so you can switch the indices around and get out the tensor back. Get out a tensor back. And then the other way would be anti-symmetry, and that would be what happens if you were to change the tensors around and you could get a minus. So what happens if we switch these around? So you could say that S is symmetric in the indices mu and nu, and A is anti-symmetric in the indices mu and nu. So some examples of these, we might say. What's a good example? Hey, I'm learning Lie algebra now. I'm one of the cool kids. Lie algebras are ridiculous. So here's an example. The metric tensor. Both that metric tensor and its inverse are both symmetric tensors. An example of an anti-symmetric tensor would be a Levi-Civita tensor, as well as a field strength tensor F. We're going to be talking about that in a little bit too, because we're going to be doing electricity and magnetism stuff today. We're going to show how you can write electricity and magnetism in two small condensed lines very simply by using our nice tensor notation instead of all of the Maxwell equations. All right, so let's talk about a couple more things. How about trace? So trace is pretty much add up the diagonals. However, there's some subtleties to that. Okay, for instance, we talked about rank, and now we're in Sean Carroll's book, so we're going to be using a lot of Carroll notation. So the metric tensor is going to be written as eta instead of g, or like a Greek letter that looks like n, even though it's eta. And then, yeah, so let's show why it's a little bit weird. So, for example, you need a tensor to be a certain type of tensor. So we need a tensor to be a 1-1 tensor in order to have a trace. And then you could say that the one way to write it would be to denote it as the following, where you have an index at the top and bottom, so there's a covariant and a contravariant index, and those are summed over because they're the same index. So really, this is just saying you are summing over the the diagonals. So if this was some matrix, or yeah, so if X was some matrix, you know, A, B, C, D, 0. 0 is everywhere else. Then what we're doing is we're summing over the indices. So this would just be A plus B plus C plus D. And the indices have to be the same. That's why they're both lambdas. So that's why we add them. That's why we contract them and add up the diagonals. Bye, Justin. Have a good weekend. Thank you for all the contributions for the stream today. That was fantastic. Hi, Sarah. Hey, it's good to see you. Good to see you. I haven't seen you in a while. Let's see. By the way, do we use Einstein notation at all? Well, establish any algebra notation. Kind of. Like we are summing over indices that are like, so we just don't write them. Like we'll write this instead, and that's just the summation over the like index. So in that sense, we're doing Einstein summation. So yeah, so technically we have been doing a lot of Einstein notation, but we don't really talk about it too much. Sean Carroll does say a little snippet about it. We did talk about it a little bit right in the beginning. We did talk about it in the beginning of the series, but not much. We just said a little bit about it because it's more about, yeah, but you do add over all of the indices. So what Einstein summation is, if you are just tuning in and you missed some of the beginning, I mean for relativity in general. Yeah, so what if you see two indices that are the same and there's one on the top and the one on the bottom, you contract them, which means you add over all of those things that are multiplied together. So for this, we want indices, the indices that are the same to add. So we can write X as a matrix where, you know, the indices 1, 1 would account for this. You know, this would be 1, 1, or for us, this is 0, 0, this is 1, 1, and this is 2, 2, and this is 3, 3. Those are the things that make up this, you know, lambda, lambda. And we add over those because it's contracted up top and bottom, right? So how does that look like? Well, then that gives us another thing. What if and this is right in the notes too, because this was a good segue into the next part of the conversation. What does a trace look like if we're talking about something with different tensors? So if we have a rank 2 tensor like this, so this is a rank 2 tensor, but it's not in this arrangement, right? We don't have a top and a bottom, so how can we contract and do the Einstein notation? Well, we can raise and lower one of them, right? We can actually write it like this. So let's say we want to change it, so we're going to change it in the following way. We can write y with a mu and a nu is equal to g mu nu times y mu nu. So the metric tensor will lower one of those indices. Oh, I'm sorry, I wrote that wrong. I was looking at the wrong thing. G nu, y nu. Oh man, I did it wrong. Well, yeah, I should do it the same as the notes. I know they're just dummy indices, but I want to make sure I get them right. Lambda nu, lambda mu. I am doing tensors, Kurt. I am. God, I admire a man who uses the old blackboard. I love the blackboard. I love my blackboard and chalk. This is a fun place to be, is right in front of a chalkboard. Okay, Okay, so we have this. So we can raise and lower the tensors as we please using the metric. And of course, it's going to be a different tensor. So that's the big thing, right? Now we have something different. We have those nice type 1-1 tensor, still rank 2, but type 1-1. And we can talk about now we can talk about taking the trace of this tensor. So you may think, what do you do with the metric tensor? Is it traceless? And if you were to say, so let's do a little bit of a recap. And what if I said, what's the trace of the metric tensor? Okay, metric tensor being a -1, 1, 1, 1. So you would think, hey, Seno. No, not really, Kurt. The ballet dancer at a bar, he goes back to the blackboard. Makes me think someone is going to get hit in the head with the eraser. Brings back childhood memories about talking in class and getting pegged with an eraser. Oh, man. Yeah, I use the rags instead. They collect a lot of the dust so that I don't inhale it. But it's just chalk dust. It's not bad. Okay. So you would think that if it's just a -1, 1, 1, then you could add those components. So the trace of the tensor you would think is -1 + 1 + 1 + 1. So that should be what, 2? But that's incorrect, right? That's not how trace works for a metric tensor. Why? Because we need to change the metric tensor to be a rank 1, 1. So how do we do that? Well, in order to get the trace, we need to multiply it by its inverse. Ugh, I think it's supposed to be like that. And then that is equal to the delta function of mu, mu. And now we can take the trace of that, which will be 4. Because we're adding them together, and then or multiplying them together, and then we're adding the exponents. So really, we're multiplying -1 by -1, and then 1 by 1 by 1 by 1 by 1 by 1, adding them all together, and we get 4. This is a 4-dimensional metric tensor, so we have the trace is 4. But in n dimensions, if you have the Kronecker delta, and you're taking the trace of it, then it's just going to be n, right? I mean, that makes sense. It's all going to be ones. It's ones all the way down. So we do need to do one more tensor thing, and that's talk about partial derivatives. And Xvention could help me with this one, because this one was fun and new. But in Minkowski space, we have partial derivatives that behave nicely, right? And we can write them as tensors and everything goes well, but that doesn't always work out the same way in some arbitrary metric on a manifold. And that's when this starts to get really complicated, or not complicated, but that gets different and difficult. So for instance, partial derivatives in Minkowski space are exactly what you expect them to be. You can write them as tensors, and they look like this. A tensor, you just write some arbitrary tensor as a partial derivative, a rank 1 partial derivative applied onto some vector. And now we can, or a metric, or a matrix or whatnot. So we can write it like that. But the interesting thing is in Minkowski space, it transforms properly under a Lorentz transformation. So it works well with space-time. Like we want that. With flat space-time, it works well. It meets those Lorentz transformations. But this is not generally true in general space-times. We will have things that do transform just like we expect them to. There could be the partial derivative of a scalar. That's going to transform just like we expect it to. And also we can still say that they do transform well, but they don't transform like we expect them to, like Lorentz invariant and other things like that. They just look differently. Partial derivatives on other metrics look differently than we normally see. But that's not to say we can't do things with them. So the partial derivative will take a KL tensor, so we have a KL tensor, and bake it into a KL plus 1 tensor. So that's what it will do. Those are the types of tensors that will change. So now we have a good idea of everything we need to evaluate something. So let's do an example of when tensors help us understand something, right? And we're going to do that by trying to find something that we know very well and rewrite it using tensor notation. So that way we can understand it in a different way or just more cleanly. Here, let's just do this. Let's just do Maxwell's equations. I think it's in here anyways. Maxwell's equations, we know them as the following. We know and love them as the following. We have the gradient times, or the curl of the magnetic field minus the partial derivative of t is equal to j, the current, right? And we can, am I on the right page for this? How did I get to such a wrong page? I specifically held this page open on purpose. These are 3 vectors, right? They're not 4 vectors, they are 3 vectors. J is the current, and then we also have the charge density, which is the divergence of the electric field. So these are the old Maxwell's equations that you know and love. I'll write out for you in LaTeX on Discord. Okay, nice. Euler and Schwarzschild comes to mind for the OG Russian pronunciations. When tensors can help us, gestures to blank board. That's funny. They can help us. They can be helpful. So we can also take the curl of the electric field plus this derivative, this partial derivative of the magnetic field, set that equal to 0, and then the curl of the electric field is also 0. So these are the famous Maxwell's equations that Maxwell worked on. Which, I don't know, actually. That's a great question, Pretz. I don't know. I don't know where the Maxwell's equations get used in like particle physics or GR or anything like that. Maybe somebody could help and understand. Integral greater than differential. I don't know. I might go with, I might agree with you on that one. I do like integral form. I might agree with you on that one. That's funny. Okay, but we can write them in tensor notation in derivative form or in differential form, and that's the following. We write the Levi-Civita of J of the magnetic field. Whoa, switched those around. Let's change that. So I already told you that the cross product can be written in terms of the Levi-Civita, and then you can add the curl comes out right here, which is nice. And then you can take it by the 0th derivative of the electric field, and this is equal to the current. We can also write this as, you know, the ith derivative of ei is equal to jo. So if we were to write the current as a 4 vector, then the density is going to be the time spot. Oh, and then I'm writing the wrong thing again. Okay, and then we can keep going with another Levi-Civita for the I. K plus the derivative, and then lastly this one. So these are nice. There's like, this is the tensor notation. So this is the this is the classical notation from like the 19th century when he first wrote it. Then we could rewrite it knowing what we know about tensors from the 20th century and rewrite it in some nice shorthand tensor notation, right? But then we can even do better, okay? And we can see if we can get it to even smaller degrees. I'm going to leave that one up, but I'm going to erase this one, okay? And the question is, oh, and by the way, don't worry about raising and lowering tensors. Because we have a bunch of 3 vectors here, we can raise and lower them however we want. All right, so now let's see if we can talk about everything in terms of the field strength tensor. So if we have the metric, or the field strength tensor, so I don't know why I said the metric, we could have this written out as negative E1, E2, negative E3, and that's the different components or whatnot. Negative B3. So this is that the metric. Geez, the field strength tensor negative B2, and here's B1, and here's B2, and here's negative B1. Now, do you notice anything? Covariant equal contravariant, very good. What is true in this world? What are we referring to? I don't know. I don't know, man. But this is an anti-symmetric tensor, so that's going to be very helpful soon because we're going to need some fancy notation. But let's just give it a try. Can we write this in tensor notation? And let's try here. So let's look at this. What is f0i equals to e to the I? Does that help us? Well, sure, it helps us. And then we'll do another one. Fij is equal to Levi-Civita ijk of b to the k, of bk. So let's do a little example of this. What's f01? Well, that's supposed to equal, so let's go to the 0, 1 spot, so 0, 1. Oh, but that's not very helpful because look at, this is down here and this is up here. So that's a big issue. So how do we lower tensors? If we're going to be talking about 4 vectors, how do we lower the indices? Well, we have to start multiplying it by the metric tensor. So we'll multiply it by 2 metric tensors, and using our Einstein summation notation, we can figure out what it is. So this is actually equal to this times this times this. What's the 0, 0 spot for the metric tensor? That's -1. What's the 1, 1 spots for the tensor? That's 1. So we have -1 times our spot here, and we get e to the 1. So this becomes e to the 1, e to the 1, e to the 1, e to the 1. Something like that. What am I doing? E to the 1. There we go. Cool. Okay, so that's what we get. So when we contract those, we'll get 1 left. Okay, I think I got that right. But anyway, so this is what we get. And then we get the spot, the negative e to the 1. I don't know. Anyways, you can see where it makes sense. Good question. Oh, yeah, we already did that in Euclidean space. Okay, so we're still there. Okay, so then we can also do another one. What's this one here? And this. Let me just write this down so I don't forget it. But that's equal to e to the 1. Okay. Now what's the next one? And the next one is f of 1, 2 is equal to the Levi-Civita of 1, 2, 3 times b3. Well, what's the Levi-Civita of 1, 2, 3? Is it +1 or -1? Well, this is an even permutation of 1, 2, and 3. So that just means it's +1. That's by definition of Levi-Civita of b3. So that works out well too. Okay. So there we go. So now we have our couple examples of how this works. We see that this works well. Yeah, so then can we do anything? Well, let's write the first 2 of Maxwell's equations. So the first 2 of Maxwell's equations become the following. The partial j applied on Fij minus the partial of F0i, and that equals ji. The second of the 2 equations is going to look like the following. F of oi, and that equals j of 0. So there we go. So can we even get even smaller than this? And the answer is yes. We can make some nicer. E is less than, if you ask me. So we can make this even smaller by, or making this even more condensed by saying, well, we can actually write this as the following. So now we can have a nice small notation that takes care of the first 2 of Maxwell's equations. So it's just really nice how we can take something complicated and put it in through a bunch of different things. So if you ask me, what method I would say, and we can do the same one. We can do the same thing for the last two equations, for equation 3 and 4. So that's these two down. And we can do the same thing for those two by writing it the following way. I didn't go over this, but you can just Google how parentheses and brackets work in tensor notation. And it's I can explain it to you really quick. And this would be part 2, and that covers equations 3 and 4. So the brackets down here basically means that you write all of the combinations out. So you'll have d mu f, and they're anti-symmetric because we know that it's an anti-symmetric thing. So this is going to be minus d mu f of lambda nu plus dot dot dot, and you just keep changing these around. So then you can switch these two to get to plus, and then you can switch these two to get to minus. And then you add them all together, and you realize that this can actually be rewritten as the following: d mu f nu lambda plus d nu f lambda mu. I'm going to move chat in a second. Sorry if it's in the way. Lambda times f mu nu, and this all equals 0. Okay, so you can rewrite it like this. You'll find out that this will simplify because you end up, because they're symmetric, you can rewrite this as the negative form, and then they'll add together and get 2, and then you can divide both sides by 2, and the 2 goes away. You'll find out that this simplifies to this, and you can rewrite it all like this. It's very nice, easy 2 notation, 2 equations that cover all of Maxwell's equations. And this is just the power. Oh, I said I would move chat. And this is just the power of what we can do with tensors. Condensing is particularly useful when you are running out of blackboard space. True. Excellent. Everybody goes, you gotta roll with it. Making sense. So m squared equals, oh geez. Cursed mathematics. So m equals e QED. That's funny. So this is just taking, we can recast everything in E and M as tensors.